Welcome to the Nanovation podcast. Information about this and other episodes can be found at fillerlab.com/nanovation. If you like what you hear, be sure to tell a friend or leave a review at Apple Podcasts. It really does help. I welcome your thoughts and suggestions. You can contact me on Twitter at Michael Filler or via email at nanovationpodcast@gmail.com.
I'd say with most small companies, if you look at what they originally thought they were going to do and what they actually do as a product, number one, the development time is really long. And oftentimes there's all these twists and turns, and often what you end up being successful with may look nothing like where you started.
That's Bob Hamers from the University of Wisconsin at Madison, talking about Silatronix, a company he co-founded with his colleague Robert West to commercialize a new electrolyte for lithium-ion batteries. On this episode of the Nanovation podcast, Bob shares the story of Silatronix's founding and the scientific twists and turns that led them to their current electrolyte design. Bob also talks about the NSF-funded Center for Sustainable Nanotechnology, or CSN, which is a multi-institutional partnership devoted to investigating the fundamental mechanisms by which nanoparticles interact with biology. The show ends with a fascinating look at the esoteric field of solvated electrons and the potential of these tiny reactive species to perform chemistry in entirely new ways. Bob has a remarkable ability to operate in areas across the technological spectrum, from tech translation to very fundamental chemical science. It was a joy hearing about his experiences, and I'm confident you'll feel the same way. This is the Nanovation Podcast, an exploration of big innovations emerging from small things. I'm Mike Filler, your host and a professor at the Georgia Institute of Technology. Enjoy the show. So it's a real pleasure to have Professor Bob Hamers from the University of Wisconsin at Madison on today's show. So welcome, Bob.
Thanks very much. Glad to be here.
Pleasure to have you. You are the Steenbach Professor of Physical Science, as well as a Wisconsin Distinguished Professor at Wisconsin. How did you get those fancy titles?
Well, let's see. So the Wisconsin Distinguished Professor Program is one that's targeted toward faculty who have strong industrial connections. And so I've started up my own company and have had a lot of interactions with industries big and small. So that's sort of a designation to recognize faculty who are engaging with the local industry. And then the Steenbach is a kind of competitive 10-year chaired professorship for somebody in the physical sciences. So it's kind of done by an application.
I see. And just to be clear, Bob is a professor of chemistry.
Yes.
And then these are additional nice things to have. So
right.
We'll talk about your directorship in a minute. I'll also point out you are the senior editor of Accounts of Chemical Research, which is a really well-regarded review journal in the chemistry space. I'm going to say real quick that, and I think you probably know this, but I was introduced to you when I was I actually don't think in person, but I was introduced to your work as a student when I was a PhD student, because the lab I was in had a friendly competition with your lab in a particular area of chemistry at the time, and maybe you could take a couple seconds to talk about what that was, the functionalization of surfaces.
Sure. I mean, I think one of the really interesting things that both you and I have been interested in is understanding connections between the chemistry of extended solids, and these include things like, in particular, germanium, silicon, and diamond, the group 4 elements, and trying to establish connections between those and organic chemistry. So when organic chemists want to make bonds, they have all these different named reactions, and there's a class of reactions called cycloaddition reactions that form carbon-carbon bonds. And I think you and I were both interested in the idea of, can those same fundamental concepts and mechanisms be applied to silicon? or carbon in the form of diamond, or germanium, right? The other elements that have roughly the same bonding. So it's a very fun time, right? It kind of making these completely new intellectual connections between two communities that normally don't talk to one another very much. The organic chemists on one side and the ultra high vacuum surface scientists on the other.
Right. And to be clear for those which is most people who've never worked in this area, the surfaces of some of these materials you're talking about have these structures that look like these functional groups from organic chemistry. Mm-hmm. And even though most of the reactions we all studied didn't occur mechanistically the same way, a lot of the products looked very similar to what you would get in organic chemistry. Mm-hmm. But the questions were, is it the same mechanism? Is it different? So it's very basic science, but very fun. And I remember very vividly the competitions between the quality of your lab spectroscopy and my advisor Stacy Bent's lab spectroscopy, and we're looking for very small peaks above relatively noisy baselines, but those small peaks really mattered in terms of interpreting the data. So I have very vivid memories of that.
Yep, it was fun times. I hope it was always a healthy but friendly competition, right?
Yeah, that's most of science, I think.
Yeah,
right? That's how it should be.
Right.
Can you talk really briefly about the University of Wisconsin system, kind of how many schools there are, and then about Madison in particular? I'm assuming it's the flagship school. Mm-hmm.
Sure, yeah. So actually it's in a state of flux right now, and I must say at the moment I can't tell you how many campuses there are. For a couple of reasons, but let me start by saying there are two PhD granting institutions. So there's University of Wisconsin-Milwaukee, or UWM, and UW-Madison, which is really the flagship campus for essentially everything, right? We have pretty much every PhD program you can imagine and many that you can't imagine. And then Wisconsin also has a set of four-year campuses and even two-year campuses that are spread around the state. And the reason I can't answer the question about the number of campuses, we are right now in the process of merging many of the two-year campuses together with some of the four-year campuses to create just a better defined structure. There's a feeling that we almost have too many separate campuses. And this was largely an outgrowth of the fact the system actually was a merger of two systems back in the 1960s, and politically nobody wanted to get rid of a campus that was in their district, and so it persisted for a long time. And I think now people realize for economy of scale, it's better to just reduce the number of campuses and try to improve on the administrative efficiency.
Right. Is it 10 or 30? What approximately?
It's probably close to 20 by the time you include all of the two-year campuses.
It's a lot like the Georgia state system, which at one time we were in the high 20s. I think we've consolidated as well over the years. Okay, I just give people a sense for what it's like up there in Wisconsin. By the way, how's the weather? Is it okay today?
Today it's beautiful.
Wait, is it snow tomorrow? When's that?
No, we've had some pretty bad flooding. A week ago, we had between 11 and 14 inches of rain in one day. So, in fact, there's a lot of roads that are flooded. The interstate's closed in places. So,
I assume that set records in terms of...
Yes, by far.
Okay.
Absolutely.
Okay. Yeah. So Bob and I had talked about a number of topics we wanted to cover, and I think the best way to do all of them is to start in 2007 with the founding of Silatronix. Is that how you pronounce it?
Yep. Mm-hmm.
So why don't you talk about what Silatronix is as a company, why you founded it, and we'll go from there.
Sure. Well, let's see. So I had always been involved in various kinds of nanostructured materials, and at the time I was working with a form of carbon that was called vertically aligned carbon nanofibers. It's kind of a long name, but basically it's a graphitic-like material that was formed in a nanostructured form in a way that I thought it would be really useful as an electrode material in lithium-ion batteries. So in the lithium-ion battery, you've got on the anode side, you have basically sheets of graphite, and lithium ions can slip back and forth between these sheets. And that's essentially how you store energy in a lithium-ion battery. And this particular form of carbon had some really interesting properties that I thought was going to be interesting. But I didn't really know where to go with it. I thought it would be interesting, but I had no idea how to take it to anything real. But then a colleague of mine, Bob West, who's now an emeritus faculty, and he is my co-founder in the company, literally was walking down the hallway, and he asked me one day, Bob, do you know anything about electrochemistry? And I said, well, yeah, we do electrochemistry all the time. And, we got to talking, and he was in the process of starting this company. And for various reasons at the time, there were some issues with some of the other people who were involved in the company with him that made me a little bit uncomfortable in joining it. But then it turns out that a year later, we completely restructured everything. And at that point, I joined as a co-founder of the new company, which was Silatronix. So Silatronix is essentially a company focusing on making safer lithium-ion batteries. And so I think you probably know that the flammability issues of lithium-ion batteries come from the fact that you have an anode, which is graphite, and you have a cathode, which is usually a metal oxide. And then in between, you've got this organic liquid, and it's called an electrolyte. It's very different from like Gatorade or other electrolytes that you think of in sports. But an electrolyte is just a liquid that is able to shuttle ions back and forth. And so these electrolytes that are used in lithium-ion batteries are highly flammable. And even at room temperature, there's something called a flash point. But you've probably seen pictures of batteries flaming. You can't bring a charged battery on an airplane. And all of this ties into the fact that these electrolytes are highly flammable. So my collaborator, Bob West, had developed an initial series of compounds that the idea was to replace the electrolyte with something totally new. And the name Silatronix comes from the fact that these new compounds incorporated the element silicon. So coming back to what we were just talking about, silicon and carbon have some very strong similarities, but also very important differences in their chemistry. In this particular case, by integrating at least one atom of silicon into the structure of these compounds, it dramatically reduced the flammability of the compounds.
And so I was going to say, of course, you hope that it doesn't reduce the conductivity.
That's exactly right, and that was exactly the problem
Okay.
we ran into. Silicon's bigger than carbon. And so initially what we found is that we actually had materials that were clearly more stable. You could operate the battery at higher temperature, but you couldn't charge and discharge it as quickly. And so that was basically effectively a showstopper, except maybe in niche applications where you really needed something that could handle high temperature, for example. So that was kind of where we were. And like most small companies, we almost folded a few times. And then a few years ago, we made an important discovery. Well, one was we invented some brand new compounds, and these compounds were definitely better, but still they were not as conductive as the existing compounds. And so we got very little traction from the corporate world. Basically, they said they really didn't care about safety. If you couldn't match the performance characteristics, then safety was really a secondary issue. But then it turns out we made another important discovery, which is that one of the other big problems of lithium-ion batteries is something called gassing. And gassing is this problem where these electrolytes that are used today are sort of like derivatives of CO2, carbon dioxide. They're called carbonates. And the carbonates decompose on the surface of the cathodes, and so that decomposition results in pressurization of the battery. So if you've ever seen one of these batteries, they're basically like a battery in a baggie. They're called pouch cells. And so if you look, for example, at your laptop computer, you'd see that most of the bottom of the laptop is essentially one of these batteries in a baggie. Right. And if this thing begins to pressurize, then it begins to push the bottom of the cell out, and pressurized batteries are not good. Sorry, go ahead.
I was going to say I have had this happen to one of our family's laptops.
Wow.
Where I didn't. So I've not ever figured out what it was. I'm really glad to learn, but we were having this situation where the battery was expanding and inflating and pushing because of where it was on the mouse pad, and it was literally like pushing the mouse pad of the laptop is out of the way. I mean,
Yeah,
it was
right.
pretty bad in the end. We took it out, got rid of it. Everything is fine, but it sounds like exactly what you're describing.
Oh yeah, and if that thing like springs a leak while you're running your laptop, that could be like really bad news.
Okay.
So anyway, what we discovered was that if we put about 5 or 10% of one of our brand new compounds into the traditional carbonate mix, so now we're not changing the composition drastically, that it completely shuts down this gassing problem. And by virtue of shutting down the gassing problem, it now actually improves the performance characteristics, both in terms of safety, because you don't have to worry about this gassing problem anymore, but also it means you can go to higher voltage and you can go to higher temperature because you've just intrinsically stabilized the chemistry of the battery. So that was sort of the big breakthrough, and since then it's been primarily uphill. The company's been getting lots of traction with some pretty big names in the battery field. We're still not turning a profit, but we are definitely, we have purchase orders. People are buying the compound. Probably we're going to be in something like a drone or radio-controlled car before you see our electrolyte in a real car, right?
Right, or a phone or something.
Yeah, but it's been an exciting journey.
I think it's an interesting one because the development time was long, and the number of, as they would say, the number of pivots was many.
Oh yeah.
But it's worth remembering that can work too. It doesn't have to be the thing that works right out of the gate and scales.
Right, absolutely. I'd say with most small companies, if you look at what they originally thought they were going to do and what they actually do as a product, number one, the development time is really long, and oftentimes there's all these twists and turns, and often what you end up being successful with may look nothing like where you started.
Right. There's a bunch of great examples. Like, well, it's funny. I sometimes give a lecture on failure to undergraduate students, and we all know where, for example, 3M came from, Minnesota Mining and Manufacturing, and their first material was corundum for cutting, right?
Sandpaper.
Students today think of Post-it notes. That's more of an evolution over the history of the company, but yeah, these are really interesting stories. So I wanted to ask you, though, looking back on this and the timeline and when you started, I mean, do you have any advice for people on how to figure out when is a good time to try and have a go at a company?
That's a really hard question to answer. I mean, I think you have to have kind of a confluence of three things. You need to have a good idea. You need somebody who can carry it out, and you've got to have the resources to make it happen, right? So, those things are all time dependent. I can't really say there's a magic bullet. And in reality, one of the reasons why I did this at a time was I've always been interested in this nexus between really basic research, which is what I love, but I really like to be motivated by the fact that something might actually be useful. And so, having been through the cycle a couple times, I worked at IBM for about 5.5 years before beginning graduate school as well. So I got a little taste of that. But to me, it's always been a motivator to know that I might be able to do something that other people find useful. And so that was kind of a big motivator for me for when I chose it. It was just kind of the right time and literally my colleague walking down the hall and saying, do you want to start a company? It's like, well, sure, let's do it.
Yeah, I mean, I guess if it's the kind of thing where you've had in the back of your head and someone presents you the opportunity, then you're likely to say, let's give it a shot.
Well, it was that and the fact that I had actually been on a review panel for, when you do a startup company, you can often get some federal money to start it, and they're what are called SBIR, Small Business Innovative Research Grants. And I had actually been on the review panel for some of these, and I thought, I could write one of these grants pretty easily. They're much easier to write than a standard grant. So it's like, well, maybe this is another way of being effective as a scientist is to think about a company, alternative ways of doing some funding of that, and you can still do great science, right?
Yeah. Oh, certainly. I think, I'm a chemical engineer by training. I think the intersection of science and engineering is really important. And there's not enough that goes on at that interface. And, we'd all talk about the valley of death. And I mean, that is a valley of our own making.
Oh, yeah.
Right? Because of how we've siloed fundamental research and applied engineering and commercialization. And I think, I think most people would agree that several decades ago, it wasn't like that, right? Everything was much more interconnected. And there's benefits to both sides of this. But I think we have to get more nimble at crossing the valley of death, probably in both directions, right? When you have a new product that you're trying to develop, realizing when new science needs to happen to get you where you need to go. And then the other way, when new discoveries happen, better translating them into products.
Right. I mean, if you go to Japan, for example, or China, you see much closer integration of companies with universities. You'll often see corporate workers working in a university environment. Companies will often pay their workers to come and do some fundamental research at a university. We just don't see that here in the U.S. There tends to be much more concern about conflict of interest and intellectual property barriers more than thinking about working cooperatively.
Have you ever seen it's a presentation, you can watch it on YouTube, called The Secret History of Silicon Valley?
I've not seen that one.
It's worth your time. Steve Blank, who is, you might have heard of him, he's kind of like a serial entrepreneur. He gives it. It's a really interesting look at Silicon Valley before the microprocessor. And so it was kind of in World War II, radar and that kind of stuff. And he talks about Stanford's rise, and basically one of the key things that fueled it and Silicon Valley was, I forget Terman's first name right now, but Terman, who was the dean of engineering, basically saying, look, stuff that's developed in our labs, you companies come to the Bay Area, come to Silicon Valley, which wasn't called that then, but come to the Stanford area, come to Palo Alto, and just use whatever you want that we've done here at Stanford. So there was never this IP barrier that there is today. And at least in that presentation, he attributes a lot of the early success of Silicon Valley to that collaboration.
I see. Cool.
Okay, so Silatronix, or any battery company, is going to use a lot of material for the applications like cars, particularly cars or transportation. Phones is a lot less so. And so you're producing a lot of material, and then questions of sustainability emerge immediately from that. And it sounds like those questions led you to other things you've done on the research side in terms of sustainable nanotechnology.
Right.
So tell us a bit about that.
Sure. So again, I've also always been interested in environmental science and understanding what happens to the materials when they get out there, right? So in the energy field, I mentioned that, for example, in the lithium-ion battery, you've got an anode, which is graphite, but you've got a cathode, which is metal oxide. So in your laptop and cell phone, it would be lithium cobalt oxide, LiCOO2. And the emergence of electric vehicles is pushing new materials that are typically more like nickel oxides or mixed compounds like what's called NMC, nickel manganese cobalt oxide. It's a more complex chemical compound. So and so these things are integral to the proper functioning of the lithium-ion battery. And so one of the questions right now is, well, if these materials are being rapidly manufactured in large amounts, are they things that we need to be concerned about in terms of environmental sustainability? And just to put things in perspective, there was a few years ago, there was an analysis of nanomaterials in the environment, right? So people are often concerned about nanomaterials because when you get to a nanoparticle that's, say, smaller than a few hundred nanometers or less than 100 nanometers, which is the official definition of nanomaterial, they begin to interact differently. And in fact, nanomaterials can be taken up into cells in some cases. And so there's a lot of concerns about whether these materials will induce other kinds of health hazards or effects in the environment. So I myself don't do anything related to human health, but of course, lots of organisms in the environment. And so there are questions about nanomaterials in general. Now, Up until recently, most of the nanomaterials that people had studied had been things that were, I would argue, relatively simple compounds. Things like titanium dioxide, zinc oxide, carbon nanotubes, things that are maybe one chemical composition, things that weren't particularly reactive. And the amounts of those materials, really up until a few years ago, most people thought of nanomaterials, or at least what are called engineered nanomaterials, meaning nanomaterials that aren't naturally present in the environment, that these things would be present in small quantities. They'd be kind of laboratory curiosities. The idea of using these materials in commercial technology has really only been around maybe about 10 years. And especially in the energy field, these materials really contribute very greatly to the technologies. In the case of a lithium-ion battery, for example, if you make the cathode and anode materials, if you make them small, if you make them nanoparticles or small microparticles, that's important to being able to charge and discharge the battery fast, for example. If you don't have to move a lithium-ion very far, it can go faster. So the idea that you could maybe have a car that could be charged up in, like 5 minutes at the gas station rather than a few hours as it is now. One way of enabling that is to make these materials in nano form. So I've been interested in this, and a few years ago I was fortunate enough to get funded on a new center funded by the National Science Foundation. By the way, everything I say here is my own opinion, not NSF. But I was fortunate enough to get funded with about 15 collaborators to investigate what do nanomaterials do in the environment. And one of the things we really wanted to focus on was next generation nanomaterials. So what are the things that are going to be used in technology applications 5, 10, 15 years from now? So this rapid expansion in the use of electric vehicles is one that we're interested in, largely because the amounts of materials are large. And just to give you an idea of scale, the estimated manufacture of things like these nickel, manganese, cobalt oxides is on the order of 500,000 tons per year in the early 2020 timeframe. So like 2025, 2023, something like that. So that's a lot of material, right? And so we're interested in understanding what kinds of chemical transformations might these materials undergo. Indeed, are there significant safety? I'll use the word risks. Risk is really a confluence of three things. One is how much material is made. So in the sense of, is there likely to be enough distributed in the environment that it might actually have an effect? Number two would be like, is the material inherently toxic, so that if the material did get into the environment, what would be the effect? And the third one is really like, what is the mechanism of exposure? So if something is always tightly packaged or integrated into something where it's unlikely to be released, then also it's a relatively low risk. So anyway, we've been interested in understanding in this, among other things that we do within the center. This is not the only thing that we do, but in this large grant that we were recently funded on, we've been looking at what do these materials do.
Okay, so let's get to a specific example in 1 second, but I have two kind of high-level questions. Because I feel like we've seen similar things with chemicals in the past, and that is, once we realized there could be downsides of using chemicals in various applications, we started to look at them and study their effects on human health, for example. Mm-hmm. But I feel like in many cases, at least the ones I'm familiar with, lots of the times where something happens or goes awry is unintended or unexpected kind of situation, mm-hmm. whether it's like asbestos and the aspect ratio, or leaded gasoline, or even MTBE in the groundwater. Mm-hmm. So how do you, the world's not perfect, so we're always going to try and find the best way to do something. But how do you balance that? Is it just by learning and understanding mechanisms you're able to predict and get some sense for what's good and what's not, and then you just say, I've done as much as I can?
Right. Well, let's see. So I guess there's two things. One is, maybe if you understand mechanistically what's going on, you might be able to use that understanding to develop a new material that might have improved properties, mm-hmm. but might have less adverse impact in the environment.
Right.
I mean, that's one dream, would be able to do that. That's not always going to be possible, right? But sometimes just by virtue of understanding what are the risks, you begin to understand, well, what do we need to do? For example, a great example right now is lead acid batteries, right? Everybody knows lead is highly, highly toxic, and it is used in automobiles, right?
Yep.
But it is almost completely recycled. Something like 85 to 90% of the lead ends up being recycled, right? So then you've got a very controlled situation where even though you're using it, it's not getting dispersed into the environment in amounts that are significant. If you look at what's happened in the lithium-ion battery field, these materials are pretty cheap. So cobalt can be expensive, but replacing cobalt with nickel and manganese to make these more complex materials like these so-called NMC materials, the driving force is to make the cost really, really low. And as you make the cost low, there's really very little economic incentive for recycling anymore. So then you get into this interesting question of understanding and balancing the potential environmental and health risks against the costs, for example, of recycling. So a big question right now would be, well, there isn't any national infrastructure for recycling of lithium-ion batteries. Small consumer batteries probably mostly end up in landfills, which is not a horrible situation if it's a properly managed landfill. But if you can imagine the amounts going up by orders of magnitude, especially in countries like China and India, which have committed to almost 100% electrification. We don't see it as much in the U.S., but Germany and other European countries as well. So the question then is, what do we need to do in terms of regulation or legislation, or just promoting good sustainability practices? Like, what can we do to put in place an infrastructure for recycling such that even if recycling isn't economically beneficial, maybe it becomes the right thing to do, right, in order to protect the environment. And that's where understanding these factors that we're looking at can play a role no matter what. Even if we can't come up with a better material, at least we can contribute to how, other methods that we can improve sustainability.
Yeah, it reminds me a lot of also First Solar, who makes cadmium telluride solar cells. And both cadmium and tellurium rare and can be toxic if they're in the right form. And so covering your roof with this material is, if it's encapsulated, probably pretty fine. But you're probably not going to want to throw that into a landfill when you're done with it. So recycling is important.
Right. Sure.
The other thing I was curious if you knew much about is in kind of differences in philosophy in different parts of the world. I get the sense that in the U.S., it's usually, we're going to do it, and if down the road we find it's a problem, okay, we're going to deal with it. And that in other parts of the world, maybe in Europe, we're going to do a lot more testing ahead of time and try and head these things off before they become problems.
Well, there's certainly some truth to that. That's an area I personally don't have a huge amount of direct expertise with. It is certainly true that in some of the developing countries, and again, in particular in this field, the rapid increase in renewable energy is really happening in China, right? China is going full force, largely because their air pollution problems are so bad, right? Going to things like electric vehicles doesn't necessarily do anything in terms of CO2 use. You still got to burn coal or something to make electricity. But where they do help a lot is in particulate matter. So given the fact that there's a lot of very heavily populated areas, a lot of air pollution is tied to particulate matter that comes from internal combustion engines like cars. The fact of the matter is you can make things better. So I think in countries like China and maybe to a lesser extent in India, the idea of very aggressively moving forward with electrification, because I think they feel that the improvements in air quality will be much more significant than any potential downside in the short term due to materials like these cathode materials.
Right. That makes sense. Okay, so let's talk a bit about some of the latest science in this space. I had seen on the CSN's website a paper that you were co-author on titled Influence of Nanoparticle Morphology on Ion Release and Biological Impact of Nickel, Manganese, Cobalt, NMC oxide, and complex oxide nanomaterials.
It's a long title.
It's but very descriptive, which is good. So can you walk us through a bit about what you describe in that paper?
Sure. I mean, so one thing we're trying to understand globally is if we have nanomaterials, what are the molecular level factors that influence what they do? So, for example, a lot of these materials that are used in lithium-ion batteries, I mentioned, like graphite, these metal oxides have very unique crystal structures where they're two-dimensional compounds, and lithium can slip between these sheets of cobalt oxide, for example. So imagine a layered structure, like a set of pancakes, right? Mm-hmm. You've got COO2, cobalt oxide, and then a layer of lithium, and then a layer of cobalt oxide, and then a layer of lithium. So these compounds have different, depending on how you look at them. So if you look at them from the top, you'd see like a sheet of paper. And if you looked at them from the side, you'd see like the cut edges of a sheet of paper, right? Yep. And oftentimes in chemistry, depending on how the detailed chemical bonding occurs at these kinds of systems, you might expect that this flat sheet of paper would typically be much less reactive than the edges, right? And I like to think of it in terms of cut bonds, that the edges of the ream of paper are like cut bonds, and you have many more cut bonds at the edges than you do at the top of the piece of paper. So the same thing is true in chemistry, kind of a general concept. So what we've been trying to do is understand if we can take nanomaterials, and we can make nanomaterials in different shapes. We can make them sometimes in pancake structures. We can sometimes make them rod-like. We can make them round. What difference does it make? Does this somehow affect the way that the nanomaterials get into the cells? And in this particular study, what we found was that much to our surprise, it did not. And that was really totally contrary to what we typically see. Typically with a sheet-like compound, the large sheet-like structures are usually less reactive than taking that same thing and compacting it into a block, right? The block would have less of the top sheets and more of the cut edges. Mm-hmm. So what we found anyway was that it actually did not make much of a difference. And what actually mattered was the surface area, that if we simply measured the total surface area of the material, that we could actually predict what was going to be the impact, both in terms of how much of the metals were released, but also what was the biological impact of the material. So this is kind of important because in the field of nanomaterials, a lot of people feel that we don't have any predictive capability, that there's many variables you have, and if you somehow have to test every single combination, it becomes completely burdensome to try to develop any kind of predictive ability. So this was one small example where we showed that we actually could develop a predictive ability if we simply knew one parameter, which was the surface area of the material, that dictated the properties. Now, that ties into all kinds of other things like some deeper understanding of the fundamental mechanisms that are going on, like why is it true that it doesn't matter in this class of compounds, whereas it normally does matter. So,
right. Could you talk a bit about how you went about determining that?
Yeah. So let's see. So what we typically will do is take these materials. So typically we make them and we can synthesize them in these sheet-like forms. So a sheet is like it almost looks like cornflakes. That's the way I describe them. They're little nanoparticles that are maybe 120 nanometers in diameter. So that's about 100th the width of a human hair. Usually a human hair is about 10 microns or 10,000 nanometers. So these are maybe 100th that size in the long dimension. And in the thin dimension, there may be only 5 nanometers. In fact, you can count the number of atomic layers in these things. But they're kind of crinkled a little bit. So they're more like cornflakes, right? So you got like a bunch of cornflakes in your bowl.
Is there something about the structure that gives the crinkling?
I think it's because under the conditions that we make them, I think partially because you have like 2 or 3 different metals involved. Uh-huh. And so the different metals like to have slightly different local bond lengths. And so they kind of make the material almost like crinkle on an atomic scale.
Okay.
Right? Okay. I don't know that for a fact. That's my working hypothesis. But in any case, they definitely crinkle. So anyway, we take these materials and we can take these flakes. If we heat the flakes up to a certain temperature, we can convert the flakes into a block and also intermediate structures. And so we take these materials then with a given mass or a given surface area, And to measure the environmental impact, we usually, well, depending on what the organism is, but one of the first passes we often use is a bacterium called Shewanella onidensis. And this is done in the laboratory of my collaborator, Christy Haynes at the University of Minnesota. So Shewanella is an interesting bacterium because it's basically at the base of the food chain. It's a soil-dwelling bacterium. And so if you imagine, suppose you have a bad landfill, for example, and the material gets into the soil, what is going to be in that soil? And well, it's going to be bacteria. And then things are going to eat the bacteria, and then things are going to eat those things, and pretty soon you're going to move up the food chain. Mm-hmm. So understanding what happens with the Shewanella is an interesting thing to do. So actually we essentially measure the respirometry, or Christy actually measures the respirometry of the bacteria. So literally what you have is a flask that's got a bunch of these bacteria in it with a little broth of nutrients, and you measure their breathing. So when bacteria are growing, they're taking in oxygen and giving off CO2 just as we do. And so if these things are sitting in a flask, you can measure the rate at which they are using the oxygen. And so that's a measure of their metabolic activity. So we can basically measure that as a function of what we put in the medium. And that then tells us about what is the effect on the organism. And again, that's one way of doing things. There's many other ways and a number of other organisms that we look at, but that's kind of a really nice, very simple way of looking at biological impact.
Yeah. I was going to ask if the center does any of the kind of life cycle sustainability kind of work. It sounds like the answer is probably no. You focuses on the biological side. But that's another aspect of sustainability that is also important, particularly for the energy applications we were talking about earlier.
Right, absolutely. Our particular center is funded by the National Science Foundation's Chemistry Division, and so we've been asked specifically to really focus on really delve into the details of the detailed molecular mechanisms that are involved. There are other centers around that have focused on the kind of the bigger picture, but we're a little more narrowly focused on the chemistry side of things. But with that said, we do think a lot about other things. So the center isn't just looking at these complex oxides used in energy. We're doing other things like nanocellulose, which is again a biologically derived material. We're doing work with nanomaterials to enhance agricultural food production. So as much as we worry sometimes about nanomaterials doing bad things, nanomaterials can also do some really good things. And one of the things we've been looking at is in the agricultural world, we know that global food production is a major issue for the 21st century. And a lot of the methods that are used to reduce crop disease, for example, or to apply necessary nutrients to plants in agriculture are typically done in ways that are not particularly effective. And so working with Jason White's group at the Connecticut Agricultural Experimental Station, we have been looking at the use of nanomaterials like copper oxide, for example. We discovered that you can apply copper oxide to plants in a way that reduces disease much more effectively than what is typically done today, which is to apply copper sulfate solution. So same material, same elements, or largely copper, anyway, in terms of the active ingredient. But by virtue of having nanoparticles that don't necessarily dissolve immediately, maybe they stick to the plants or plant leaves, maybe they can absorb to the root system. We're really trying to understand the mechanisms right now, but it's pretty clear that nanomaterials can actually do a lot of really good things for the environment, for our world. And so we're trying to balance this idea of how do we make nanomaterials not do bad things, but more importantly, how do we actually use nanomaterials to really enhance sustainability and to do good?
I think that's a great point, and this is probably the case with almost all science, is that there's an upside and a downside. And I think sometimes scientists, because of what we do, where we try lots of things, and most of them are failures, and we always stay optimistic and try the next thing, tend not to see the downside as much. Mm-hmm. And sometimes when our ideas and technologies confront the real world, we run into problems. But I'm 100% in agreement that these things have tremendous positive benefits. That's why we do it. The other thing I wanted to say was, as you were talking about the plants with copper oxide, I had two thoughts. The first thought was this hilarious picture now of a whole bunch of plants being rolled into an atomic layer deposition system.
Right.
And then I had heard recently about a company called Appeal, which is not nano per se, but what they specialize in is taking stems and things like that from plants, fruit plants and things like that aren't used in the fruit, of course, taking them, chopping them up, creating a very fine coating that can be put onto fruit. It's plant-based and slows the diffusion of oxygen. It's very simple. And allows them to be picked much later and last through shipment. And if you think about what things like that do, is it can really change the food supply and the way we ship things to different parts of the world, because you can ship further and the food will last that much longer, and it does so without refrigeration, right? So these kinds of simple solutions have, particularly in food, have a dramatic impact on human activities.
Absolutely.
Yeah. I wanted to spend just a few minutes before we wrap up coming back to what I'll say is some of your more fundamental work. And as we talked at the beginning, that's where I was first introduced to your interests in the work your lab does. But the thing I want to have you talk about is negative electron affinity materials. What they are, why we might want to use them, and a little bit about what your lab is doing in that area.
Okay. So kind of a little bit of an esoteric field, but I'll do my best, right? So in any material, so when I say a material here, I mean a solid, okay? So imagine a solid, and it's comprised of protons and neutrons and electrons, and the thing's electrically neutral, but the electrons are confined within the material, right? And usually if you shine light on this, or you have all these different energy levels the electrons can be in, and when you shoot light at a material, okay, you promote the electron to some higher energy state, but the electron is still confined within the material. All right, and so that's called a positive electron affinity. It simply means the electron is still bound when it's in this excited state. So it turns out there's a small class of materials that have what's called negative electron affinity. And literally what that means is that when you excite the electron or the electrons in the material to their first, what I'll call bound state, right? So that's like an energy level. It's actually so high up that the electron would actually rather be an electron just floating out in space than it would be confined within the material. So that's great. So one of the really interesting properties of negative electron affinity materials, though, is that if you do shine light on them at an appropriate wavelength, literally you get electrons streaming out of the material, because the electrons are smart. They will always manage to find the lowest energy state, and that if that lowest energy state happens to come shooting out of the material, that's what they'll do. And so this property has been known for many, many years. It's used in a lot of different optical detectors. So the things you do in laboratory and medical instrumentation, not quite as much today, but up until about 10 years ago, essentially all optical detectors were based on this idea. But they used materials like gallium arsenide with cesium. And so kind of esoteric materials, but the important thing is those things had to be confined within a vacuum tube because they were very reactive with air and completely reactive with water. So this was something that could only happen in a vacuum. So vacuum tubes, right? All the vacuum tubes that you know about in some way were relying on similar kinds of ideas. So anyway, so it turns out that diamond has this unusual property of negative electron affinity and is also air and water stable. And so you can, now when people think about diamond, they think about materials that are like super expensive, right? Well, this is not like jewelry grade diamond. This is like industrial grade diamond that you can grow in a laboratory. So you can grow thin films of this material that are only a few hundred nanometers thick. You can make coatings over large areas. But the really cool thing is if you take one of these diamond films and you shine ultraviolet light on it, you get electrons come shooting out. And because diamond is stable in water, you can now make electrons that come shooting out in water. And they make something called the solvated electron. So the solvated electron, to a chemist, is something that we never teach we never teach in chemistry. You never hear about it in undergraduate chemistry.
Chemical engineers never hear about it.
No, absolutely not. I mean, I don't think I ever heard of it until like 5 years ago.
Right.
But it's an electron in water. It's called a solvated electron because the solvent, which is water, kind of forms a little cage around it. So kind of like a particle in a box. It's this electron with like 6 water molecules surrounding it. But it's like the chemist's perfect reducing agent. When we teach chemistry, we teach about oxidizing agents and reducing agents. And there's one theory of acidity called the Bronsted theory, which is said that everything is controlled by protons. And there's a Lewis theory of acid-base character that says everything's controlled by electrons. So a Lewis base is like an electron. So what could be a better reducing agent than an electron in water, right? So it's like just the chemist's perfect reducing agent. So anyway, what we found is that these solvated electrons have some really interesting properties. They're very effective at reducing CO2, for example. And we've even found that they can induce the reduction of nitrogen to ammonia, right? So this reduction of nitrogen to ammonia turns out it is the world's most energy-intensive chemical reaction because the scale of making ammonium-based compounds for fertilizers, coming back to the food connection, right?
Yeah.
And it's the most energy-intensive chemical reaction carried out on the face of the earth because of the amount and the energy input. And it's done industrially at really high temperatures and high pressures because nitrogen is such a stable molecule that breaking it apart in order to allow it to form something like ammonia just takes enormous amounts of energy to reach these high energy intermediates. Well, it turns out that if you have solvated electrons, you can make other kinds of interesting species like N2H, a nitrogen molecule with one hydrogen bonded to it. Turns out to be the critical intermediate. So anyway, it turns out that these solvated electrons can induce all kinds of really cool chemical reactivity that people have not been able to study before because they've never had a way of being able to conveniently make solvated electrons in water. People have been able to make solvated electrons in ammonia and some other kinds of solvents, but because they don't live very long in water, there's been no convenient way of making them.
I see. I was going to ask you what the lifetime was. Once you make them and they jump out of the diamond, how long do they hang around?
Yeah, a few hundred microseconds. So,
okay.
Not long enough to order them from your local chemical company, right? but they're long enough that you can actually, you can control what they do. So if you put in CO2, they'll react with CO2 faster than anything else. But anyway, so they enable lots of really interesting chemistry. Now I make no claims that we are ever going to replace the Haber-Bosch process for making ammonia. That's been finely tuned in scale and things. But it just enables some really kind of new and unique chemistry that people have not been able to look at before. Anyway, that we can look at using these kind of negative electron affinity materials.
I was going to say that it's always hindsight where it's like, well, that was obvious. But, when you're doing something, as you would describe, esoteric, it's not obvious where it's going to go. And that's the excitement of it in many ways for many of us. But I look at that as a fun, positive thing about it. One last question for you.
Sure.
Who are your role models?
Well, when I was a kid, my role model was really my grandfather, who passed away when I was about 7 years old. But he was the one who originally got me really interested in science. He was a machinist by training, and when he retired, he got this huge metal lathe in his basement, and he made this giant telescope that had a 12-inch diameter mirror, and it was like as long as his garage.
Wow.
But he lived in a dark area, and so as a kid, I would occasionally be able to go out there and, just look at the stars, right? Look at the moon.
That's great.
One of my biggest mentors has always been John Yates. John Yates was a surface scientist who passed away a few years ago. But he was a mentor to me and a hero in lots of different ways. But he was someone who I thought was sort of the epitome of scientific interest and being truly dedicated and interested in science, but also being a genuinely good human being.
For those who don't know, he had this book, I can't recall what it's actually titled, but this book of basically surface science techniques. And it was all sorts of, some big, some really just tiny little, you should do this when you're building a vacuum system kinds of things, that is kind of a Bible, or at the time was a Bible to a lot of surface scientists.
Yeah, absolutely. And then more recently, I'd have to say that a more recent hero is Barack Obama. I think that he has done a lot for the culture of the country, and we won't go into that here, I suppose. But anyway, that's certainly one of my heroes.
Okay, outstanding. So, Bob, let me thank you for taking us on a really fantastic journey from commercialization to nanotechnology in biological systems to really esoteric fundamental questions about electrons in water. It's been really great. Thanks. I hope you'll come back sometime.
Well, you're welcome. Thanks for inviting me.
You've been listening to Nanovation. If you enjoyed the show, please leave a rating or write a review on Apple Podcasts. Show notes are available at fillerlab.com/nanovation. Nanovation is recorded in the Marcus Nanotechnology building on the campus of Georgia Tech. Andrew Cannon edits the show. I'm Mike Filler. See you next time.